This is Physical Chemistry, Part 3, Quantum Chemistry, Chapter 19, The Vibrational and Rotational Spectroscopy of Diatomic Molecules. Section 19.1, Introduction to Spectroscopy. So first let's look at the wavelengths of photons. Over here we have a fairly narrow range of visible lights from 400 nanometers to 750 nanometers. It's right here. If you have longer than 750 nanometers, not 700, 750, it's near infrared, and then infrared, and a far infrared or far IR, and then microwave, and then radio wave. We can also go to the shorter wavelength. You get UV right here, UV, ultraviolet, and then X-rays, and then gamma rays. UV light can usually excite an electron in a molecule from HOMO to LUMO, or from occupied valence orbital to empty valence orbital. So again, UV is usually used to excite valence electrons. X-rays have higher energy and can be used to excite the core electrons. Gamma rays have even higher energy than X-rays. Now you're looking at just one photon. The photon is traveling from left to right. A photon consists of two fields. One electric field, the black one. Another is the magnetic field. Okay, the magnetic field is perpendicular to the electric field. Both the electric and magnetic fields oscillate constantly. And this photon travels at a speed of light. The direction of the travel of the photon is perpendicular to the directions of the oscillations of the electric field and the magnetic field. Right? So this is the direction of the oscillation of the magnetic field. This is the oscillation of electric field. And the third direction is where the photon travels at the speed of light. Now let's look at some diatomic molecules. Let's look at their vibrational state populations. So we have 6 examples here: H2, H fluoride, hydrogen bromide, nitrogen, carbon monoxide, and bromine 2. Right? So if you measure the infrared spectrum of each of the 6 molecules, you will get a wave number in the unit of reciprocal centimeter. Okay, why not reciprocal meter? Well, this is by convention. H2 has the largest wave number, okay, 4400. Oh, by the way, by convention, one wave number is 1 reciprocal centimeter. Okay. Hydrogen fluoride, 4200, hydrogen bromide, 2600, nitrogen 2, 2400, carbon monoxide, 2200, bromine 2, 300. Okay, why is this number much smaller than the other numbers? Okay, remember, if you have a harmonic oscillator, its frequency is 1 over 2 pi times the square root of k over mu. So for this bromine 2 molecule, you have a very large mu. At the same time, you have a very small k, because this is a double bond. This is a triple bond. This is a triple bond. All right? And these three are single bonds, but these three single bonds are all much stronger than bromine single bond. Because hydrogen atom is small, the radius is small, the bond distance is the sum of the two atomic radii, so the bond distance is small here. That means usually you have a stronger bond with a short bond distance. Okay, bromine atoms are really large. Therefore, the bond length is fairly large. So that's another reason why you have a small force constant here. So again, the oscillation frequency of bromine 2 is much smaller than others. And also, the reduced mass of bromine 2 is much larger than others. That's why bromine 2 has a smaller oscillation frequency. And then remember, the vibrational energy levels is 0.5 hν and 1.5 hν for the lowest and second lowest vibrational energy levels. The difference between these two levels is just 1.5 minus 0.5. That's just 1 hν. 1 hν is the energy difference. So you need a photon with that amount of energy to excite this molecule from the lowest vibrational energy level to the second lowest energy level. Alright, so it just happens the photon frequency is equal to the frequency of the harmonic oscillator. Alright, so that means you need a lower photon energy to excite the bromine 2 molecule. And that's why you have a lower wave number here. Right? Again, lower wave number, lower frequency. Wave number is proportional to frequency. All right? Oh, by the way, wave number is 1 over lambda. So when you are looking at this, that means you can put 4,400 waves within 1 centimeter. You can put only 300 waves within 1 centimeter. Alright, so this is a smaller wave number, but then longer wavelength here. Alright, and now let's look at the populations. We are using the so-called Boltzmann distribution. Qualitatively, Boltzmann distribution tells us the higher energy levels are less likely to be populated. The lower energy levels are more likely to be populated. Quantitatively, well, we can calculate the ratio between N1 and N0. N1 is the number of molecules in the first excited state. N0 is the number of molecules in the ground state. In this case, we're talking about vibration, so this is ground vibrational state. This is the first vibrational excited state. And this means we have an energy of 0.5 hν, over here 1.5 hν. So basically, we just calculate this population ratio by doing e to the power of negative 1.5 hν over kBt, divided by e to the power of negative 0.5 hν over kBt. And then you get these numbers. This very small number tells us if you have a bunch of H2 molecules, most of them occupy the ground state. All right, so about 7 out of 10 billion such molecules occupy the first excited state. Very few. Okay, 7 out of 10 billion. All right. In this case, 2 out of 1 billion, 3 out of a million, 10 out of a million, 30 out of a million. In this case, well, this is kind of interesting. So if you have bromine 2 molecules, 21% of these molecules occupy their first excited state. 79% occupy the ground state. Why is that? Well, this is because the energy difference between the first excited state and the ground state is very small in this case. Small wave number, small frequency, that means small photon energy and also small energy difference between these two states. Alright, that's why. And these numbers, these ratios are at 300K. When you have 1000K, again, the population is proportional to e to the power of negative energy over kBt. So if you have very high temperature, then you have a larger ratio here, right? So now you can see this ratio is much larger than this ratio. Basically, it tells you at higher temperature, these molecules tend to occupy the higher energy levels, okay, more likely than lower temperatures. All right, so these numbers are just larger than these numbers. All right. Okay, this is the equation to relate the wave number of the infrared photon with the frequency of the diatomic molecule. So this is the frequency of the vibration of the molecule. This is the wave number of the photon. Oh, I'm sorry. 1 over lambda is the wave number of the photon. Now you can see 1 over the lambda of the photon, well, also called the wave number of the photon, is proportional to the frequency of this diatomic molecule, approximated by the harmonic oscillate model. Okay, so I'm using harmonic oscillate model. Section 19.2, absorption, spontaneous emission, and stimulated emission over here. So now if we have a molecule occupying the lowest energy level, it may absorb a photon to jump to the first excited state. Or you can say the second energy level. All right. So we need a photon here. You can call this absorption of a photon. But also you can just call this a stimulated absorption of photon, because this transition will have to be stimulated by a photon. Although you do not have to say stimulated, because it's obvious this molecule will have to absorb a photon. So being stimulated is by default. But why did I mention stimulated? When this molecule absorbs a photon and jumps to the first excited state, it can jump back in two different ways. One is so-called spontaneous emission. It just jumps back and release that photon. Or there's another process, stimulated emission. So this molecule may be stimulated by a second photon. It comes out, it's not absorbed. This molecule is stimulated and release the photon it absorbed before. So that's why you see one photon coming in, two photons coming out. So this photon is just this photon, and then when this molecule jumps back to the lowest energy level, well, this photon was absorbed by this molecule in this absorption process. It's gonna be released in this process. All right, and then at equilibrium between this level and this level, I'm talking about the populations at this level and this level. We have this equation, all right, at equilibrium. That means the absorption process has a rate, absorption rate. The emission processes have two different rates, okay? For spontaneous emission, the rate is here. For stimulated emission, the rate is here. At equilibrium, the absorption rate is equal to the emission rate. Okay, so this is absorption rate. This is the stimulated emission rate. This is the spontaneous emission rate. The absorption rate is proportional to N1. the number of molecules in this energy level. The emission rate is proportional to the population in this energy level. All right, so specified by N2. N2 is the number of molecules in this level. N1 is the number of molecules in this level. Now, B12, B21, and A21, you can think of this three as the reaction rate constants in chemical kinetics. You can view this as a kinetic process, and the equilibrium between N1 and N2 is similar to chemical equilibrium. You can view this N1 as the reactant or the concentration of the reactant. N2 is the concentration of the product. So basically we're talking about the forward reaction rate is equal to reverse reaction rate at equilibrium. It's just there are two different steps in parallel that make contribution to the reverse reaction rate. What about this rho? Rho is just the number of photons here. So this rho is the number of photons here. Okay, the number of photons that stimulate the absorption or emission, okay, in this stimulated emission process. A21 is just the reaction rate constant for the spontaneous emission. All right, so it does not involve another photon, therefore it's just A21 times N2. This rho is simply the spectral density you learned in the black body radiation. So Einstein proved these two equations. B12 is equal to B21, and the ratio between A21 and the B21 is this. Einstein actually used the black body radiation mechanism and equations. So I would say both Planck and Einstein made a contribution to these two equations. I will not prove these two equations here. You can find the derivation in the textbook or maybe on the internet.